Hello everyone and welcome to our presentation. Today we will be talking about password cracking. But before we dive in, let me introduce my team. My team members are Jiayu Zhang, Xiangrou Zhuang, Hyoming Kim, and Shenfang Jian. Now let's dive into it. First, let's talk about history of password cracking. From 1960s to 1970s, as academic research increasingly relied on shared computer systems, the concept of password cracking emerged. At the time, the most common method was brute force, where every possible password combination was tested until the correct one was found. To 1991, Alec Moffat introduced Crack, a dictionary-based attack that tested common password combinations against hash values. This approach improved the efficiency of password cracking and could also be used to check the strength of user passwords. To 1997, Cult of the Dead Cow introduced Lovecrack, a password cracking tool specifically targeting Windows anti-password hashes. It introduced features like automated analysis and the usage of rainbow tables. Lovecrack's impact extended beyond the technique realm, as it could be used both by ethical hackers and malicious hackers. In the 1990s, password cracking marked a turning point, with an increased awareness of penetration testing, ethical issues, and legal questions. So penetration testing is ethical hackers simulating attacks to test system security. And to 2000s, advanced in hardware technology also improved the efficiency of password cracking. In the late 1990s, John the Ripper combined dictionary-based approaches with character substitution or appending numbers, significantly improving cracking efficiency. Meanwhile, Hashcat, by utilizing distributed cracking across multiple systems and GPU acceleration, could crack millions of hash values per second. Offcrack used pre-computed rainbow tables to exchange space for time, further enhancing the efficiency of password cracking. After 2010, John the Ripper and Hashcat have adapted to the convergence of advanced hardware, distributed computing, and machine learning, allowing them to handle high-complexity encryption methods like bcrypt and Argon2. However, they still face challenges from GPU-accelerated tools and distributed cloud computing platforms. Additionally, machine learning and AI technologies have introduced previously unconsidered vulnerabilities in password cracking techniques. Rainbow table is what we used in our project, which is a table that defines the relationship between hashes and password. The original password is passed through SHA-1 to generate a hash. Then a reduction function is used to revert the hash to a possible password. The step of applying SHA-1 and the reduction function are repeated until the desired chain length is reached. The rainbow table records the starting and final passwords after a series of computations. Next is about the hash collision, also called false alarm. The limitation of SHA-1 can cause different original passwords to produce the same hash. To solve the hash collision problem, a different reduction function is used in each iteration. If the same hash is produced, it can be deduced that the collision occurred during the same iteration, and different reduction functions are tested. For example, after applying reduction function R3 to the hash RE3XES, the password is not found in the table, so R2 is used instead. When applying R2 and R3 together, the password Linux23 appears in the rainbow table. Running the original password passwd with R1, R2, and R3 confirms that Linux23 is indeed recorded in the rainbow table, indicating attack success. Next, let's talk about the John the Ripper. So John the Ripper is a password cracking method, cracking passwords based on common password combinations for a specific encryption method. First, the hash value is computed. Then John the Ripper is used to identify the encryption method and perform reverse password cracking. For example, use cat to quickly search the pass.txt file to find a user AZI and hash ZWWXIH15Q. Then call John the Ripper to determine the encryption method as DES, and use the DES method to reverse the password and find the original password. Now let's talk about time memory trade-offs, which is the main concept of this project. So first look at the equation in the top right corner. Capital M represents the maximum memory usage and capital T represents the maximum time consumption. Little m is the number of chain in a single rainbow table, and L is the number of rainbow tables. M0 is the memory required to store the starting point and the end point. T is the length of a chain, and T0 is the encryption rate of plaintext. So look at the top left graph, shows the maximum memory consumption, and this surface is only influenced by the total number of chains m. In other words, by using more memory, you can use more chains to store information, which increases the efficiency of cracking. And on the bottom left graph, shows the upper bound of the time required for cracking, and this surface is only influenced by the chain length t. Increasing the chain length will increase the cracking time. Now let's look at the graph on the right. It combines the results of two graphs on the left and sets the success rate to 99.9%, which shows the overall time and memory consumption. The red surface is a combination of two graphs on the left, while the blue surface represents the most ideal state, meaning a success rate greater than 99.9% with minimal memory and time usage. The intersection of these two surfaces forms two lines, which represents the optimal solution. By examining the two intersection points in relation to the previously mentioned formula, L is the number of rainbow tables, only affect the final output efficiency and doesn't impact the concept here. Additionally, M0 and T0 are fixed constant and can be ignored. Therefore, we can observe that as M increases, the T decreases, and conversely, as T increases, M decreases, which is the specific manifestation of the time memory trade-off.
This is the demo video of password cracking. Before we run the code, let me walk you through how everything works. First, for this project, we first generated a rainbow table using the rockq.txt, which is a password list. Then, we used the table to crack leaked hashed passwords from LinkedIn, attempting to recover the original plaintext passwords. We started by applying the SHA1 hash function, which converts the plain passwords from rockq.txt into hash values. Next, the reduction function. We incorporate round num to use different parts of the hash, reducing collisions. We also apply a char set to introduce randomness and improve efficiency. Then, in generate rainbow table, we hash passwords and create chains. Here, we optimize memory usage by reducing the number of chains when the chain length increases. This allows us to test how many memory efficiency changes with different chain lengths. For our experiment, we tested 5 different chain lengths: 100, 500, and 1000, 5000, and 10,000. Okay, alright, now let's run the code and see the results. Now that the execution is complete, let's take a look at what we got. As you can see, we have loaded the passwords and hashes from the text file and generated the rainbow table with a different chain length. So you can see the results of each chain length printed in the output, and also the tested chain lengths and the storage sizes of the rainbow tables, the cracking times for each cases, and finally the number of successfully cracked passwords are shown here. Okay, after gathering these results, let's run the code to get the visualized data with the graph. First, this graph shows relationship between the rainbow table size and the number of chains, and also how chain length affects cracking time. And finally, another visualized result of the data with graphs are as follow. So this is the cracking success rate. This shows how often we successfully recover the passwords. And this cracking efficiency presents how many passwords we cracked per second. Lastly, the storage efficiency. This tells how well we optimize the space usage. That wraps up the demonstration. Thank you for watching.
In our project, as you can see, we tested 3 different methods. Hashcat got a successful rate of 11.89%. John the Ripper only managed 1.06%. And our project, using different reduction functions, boosted the successful rate to 19.85%. So, in conclusion, this attack highlights the ongoing tug-of-war between security and exploitation. As attackers continuously evolve their methods, our security measures must also adapt. Today, we rely on advanced encryption methods like SHA-3, symmetric encryption like AES, and asymmetric encryption like RSA and ECC to protect our data, providing strong defense mechanisms. In terms of defense, sorting plays a crucial role. By adding random values before encrypting data, sorting effectively mitigates the use of rainbow table attacks, strengthening security. However, these attacks remind us that security is an evolving field, and today's defenses may not be sufficient in the future. Therefore, ongoing research in encryption and defense techniques will be essential to maintaining security. Here is the end of our presentation, and thank you everyone for your listening.